The Sun is the star at the center of the solar system. It is a nearly perfect sphere of hot plasma, with internal convective motion that generates a magnetic field via a dynamo process. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, 864,000 miles, or 109 times that of Earth, and its mass is about 330,000 times that of Earth. It accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, 73%. The rest is mostly helium, 25%, with much smaller quantities of heavier element, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star, G2V, based on its spectral class. As such, it is informally and not completely accurately referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun currently fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape from its core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature, while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus, and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers, and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times, and the Sun has been regarded by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of solar calendars, one of which is the predominant calendar in use today. The Sun is composed primarily of the chemical element hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8% of the mass of the Sun in the photosphere, respectively. All heavier element, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the Sun's mass, carbon, 0.3%, neon, 0.2%, and iron, 0.2%, being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier element. The hydrogen and most of the helium in the Sun would have been produced by Big Bang nuclear synthesis in the first 20 minutes of the universe, and the heavier element were produced by previous generations of stars before the sun was formed, and spread into the interstellar medium during the final stages of stellar life, and by events such as supernovae. Since the sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy element have settled from the photosphere towards the center of the sun because of gravity. The proportions of metals, heavier element, isn't changed. Heat is transferred outward from the sun's core by radiation, rather than by convection. See radiative zone below. So the fusion products are not lifted outward by heat. They remain in the core, and gradually an inner core of helium has begun to form that cannot be fused, because presently the sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase, before nuclear fusion and the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years this gradual buildup will eventually cause the sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. The solar heavy element abundances described above are typically measured both using spectroscopy of the sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar sun and are thus not affected by settling of heavy element. The two methods generally agree well. The structure of the sun contains the following layers. Core, the innermost 20-25% of the sun's radius, where temperature, energies, and pressure are sufficient for nuclear fusion to occur. Hydrogen fuses into helium, which cannot currently be fused at this point in the sun's life. The fusion process releases energy, and the helium gradually accumulates to form an inner core of helium within the core itself. Radiative zone. Convection cannot occur until much nearer the surface of the sun. Therefore, between about 20-25% of the radius and 70% of the radius, there is a radiative zone in which energy transfer occurs by means of radiation, photons, rather than by convection. Tachocline, the boundary region between the radiative and convective zones. Convective zone, between about 70% of the sun's radius and a point close to the visible surface. The sun is cool and diffuse enough for convection to occur, and this becomes the primary means of outward heat transfer, similar to weather cells which form in the Earth's atmosphere. Photosphere, the deepest part of the sun which we can directly observe with visible light. Because the sun is a gaseous object, it does not have a clearly defined surface. Its visible parts are usually divided into a photosphere and atmosphere. Atmosphere, a gaseous halo surrounding the sun, comprising the chromosphere, solar transition region, corona and heliosphere. These can be seen when the main part of the sun is hidden. For example, during a solar eclipse,